Hey everybody, Dr. A here, and in this video we're going to be providing some background information on moment of inertia of composite shapes. And we're going to be referencing the Hibbler Statics textbook published by Pearson. But before we jump into things, don't forget to hit like and subscribe and be on the lookout for other content like this. All right, let's dive into it.
In this video, we're going to be discussing section 10.4, which is on composite bodies, moment of inertia. So if you remember, a composite body is just a shape made up of discrete, simpler shapes. So this is going to be a little bit different than a continuous body, which is an area bounded by some kind of mathematical function. In this video, we're going to be talking about shapes like rectangles, squares, triangles, circular segments, basically simpler shapes that are attached to one another to make this composite body, again, made out of simpler shapes and areas, okay? So the general formulation is going to be as follows. So what we have to do is we have to say, we're going to say I sub x is going to be the moment of inertia about the centroidal x-axis of the composite shape. Okay, so this is here the x indicates the centroidal x-axis, and we're going to write that as I sub x equals the summation of I sub x sub I plus a sub I d sub y sub I squared as I goes from 1 to n. So what does all of these symbols mean? Well, first, the I sub x sub I, okay, two subscripts, is the moment of inertia about the centroidal x-axis of each part I. So let's say, for example, you have an L shape, okay? Maybe you have an L-shaped area. You're going to have maybe two parts, a part 1 and a part 2 of this kind of L shape. And I sub x sub I is represented by the moment of inertia about the centroidal axis of each individual part, okay? And then, of course, a sub I is the area of each part I. And then d sub y sub I, what is that? So d sub y sub I is going to be the perpendicular distance, and in this case, in the vertical direction, and this is the perpendicular distance between the centroidal x-axis of the entire shape and the centroidal x-axis of each part I. Okay, so take a second and absorb that definition. D sub y sub I is the perpendicular distance in the vertical direction, that's why we call it d sub y, between the centroidal x-axis of the entire shape and the centroidal x-axis of each of the parts, each part I, okay? And then we have this summation term that kind of wraps it all together to show that we add up all of these pieces to get this overall moment of inertia about a centroidal x-axis of the entire shape. So we're going to say n equals the total number of parts of the shape. So I mentioned a few minutes ago, if we have an L-shaped area, you're probably going to break that into two rectangles. And so in that kind of problem, n would be equal to 2. Now, we're going to have the same kind of formulation. Oh, man, I hate it when this happens to the screen. There we go. We're going to have the same kind of formulation for I sub y, okay? It's just the terms are going to be a little bit different, but it's the same general formulation. So I'm going to say similarly, we have I sub y equals the summation as little I goes from 1 to n, and we're going to have I sub y sub I plus a sub I d sub x sub I squared. And each of these terms has a very similar definition. One thing to note is you have d sub x sub I that you're using in the IY formulation. And the definition of d sub x sub I is similar to d sub y sub I. It'll be the perpendicular distance, but in the horizontal direction between the centroidal y-axis of the entire shape and the centroidal y-axis of each part sub I. So maybe we should write that down because in my experience teaching this, I've seen a lot of people, the mistakes that they make are really in these d distances. So this is going to be the perpendicular distance in the horizontal direction from the centroidal y-axis of the entire shape and the centroidal y-axis of each part I. Okay, so similar definition, but in a different direction. Okay, now the great thing about composite bodies is because they are made up of generally simple shapes, we are going to have some generally simple formulations for I sub y sub I and I sub x sub I, these values here, okay? Again, if they're simple shapes, we can have these pre-derived formulas. And if you recall in a previous example, we derived some of these very simple formulas before. So let's talk about some of these simple shapes, okay? So I'm going to say for a rectangle, and let's draw a rectangle out. Let's say that the rectangle has a base of b and a height of h, and then we're going to put our remember we're talking about centroidal axes now. We've got a centroidal axes, a set of axes x and y. So I sub x of a rectangle, again, this is for a rectangle specifically, is going to be bh cubed over 12. And if you remember from a previous video example, we actually derived that formula. And then we're also going to have I sub y, and this formula happens to be hb cubed over 12. One way some people like to think about these formulas, because they're kind of similar, but they are different. You have bh cubed over 12 plus hb cubed over 12. Some people think of it as you take this rectangle and you flip it 90 degrees, and it's kind of the same formula, but if you flip this 90 degrees, then h becomes the base, okay? So that's for a simple rectangle. What about a circle? Let's look at that. For a circle, of course, that's not my best circle. And let's say the circle has a radius r, okay? And then where are your centroidal axes of a circle? Well, they're right through the middle, of course. And for a circle, we're going to have I sub x equals pi radius to the fourth over 4. And then I sub y is going to be also, what do you think it's going to be? Well, also pi r to the fourth over 4. And that's because for circles, you have double symmetry, right? No matter how you look at a circle, it's symmetrical in any different direction, okay? What about a semicircle? Remember, a semicircle is a half circle, right? So let's say semicircle. So let's say you have half a circle right here, okay? So so we're going to have our centroidal axes. Where do you think the centroidal axis is here? Well, the centroidal axis is actually right here, X and Y. So notice the centroid is right here. It's not down here at the bottom. It's a little bit into that area, okay? And we got to make a note of this. This is Y bar, okay? Y bar from the base side of this semicircle. Y bar is going to be 4R over 3 pi, okay? And, oh, by the way, we have a radius r here, of course. This is radius r. And then what are our moment of inertia values? Well, we're going to have, they're actually equal, Ix equals Iy. And that's going to be pi r to the 4th over 8, okay? And so on and so forth. So there are other simple shapes as well. In fact, your textbook, the Hibbler statics textbook, if you look on the back inside cover of this textbook, there's a nice little table that has a summary of moment of inertia values and centroidal locations of all kinds of simple shapes. So you do have that readily available. Also, if you look in the NCEES FE reference manual, we also have very simple, a simple table that has moment of inertia values for all these simple shapes, okay?